Thank you. It's a pleasure to be here today in occasion of the groundbreaking for the Hillman Laboratories. I think it's a great initiative. I'm glad I'm part of it. And today I'm going to talk to you a little bit about technologies and vaccines. I will start with this slide. This slide goes back to the beginning of vaccination. It's July 6, 1885. And when Louis Pasteur basically inoculated Joseph Mister with a rabies vaccine. The page that you see there is from the notebook of Louis Pasteur, which you can find in the museum of the Institut de Pasteur in Paris. I know you cannot read, but I'll help you because it's very, in this slide, I'm trying to translate what's in that handwritten page. Basically, here you find how to make a vaccine. Pasteur knew how to make it. And basically what he says is that if you want to make a vaccine against rabies, you need to isolate the virus, the wild-type virus. And he got that from a street dog, the rabid street dog. Then, once you have isolated the virus, you need to be able to manufacture the virus in a consistent way. He basically was doing that by inoculating into the brain of rabbits 25 times until you got the virus consistently making for 20. And then once you have a consistent made the consistent virus in the brain of rabbits, basically you need to inactivate the virus. At that point, it basically took the spinal cord of the rabbits, 1 centimeter each, and put to dry for 15 days. And he noticed, and you see the translation in the table before, that after 1 day in the dry air, the virus was still virulent, 2 days virulent, but then when you got 10, 15 days, the virus lost virulence, and now was a good vaccine. Now, since that day, every single vaccine we've been made for a century has been following the same thing. And this is the way we make vaccines. Basically, what you see is that what I call analog vaccine. If you want to make a vaccine, you need to do 3 things. Isolate the virus, the bacteria, and the things, grow it, inactivate, and inject. We've been using this all the time. And when SARS came 2002, 3, basically, we wanted to isolate the virus, make vaccines. Fortunately, that's what we made at that time. But fortunately, the vaccine was not needed because SARS-CoV-1 disappeared. But then 2009, we got H1N1, the influenza pandemic. And then this was a vaccine we can manufacture every year. We know how to make it. So we immediately rushed to make a vaccine. And you see in the slide, the red line, we were very good. In 8 months, we had enough vaccine to distribute. But if you look at the blue line in the left, the peak of the virus was a few months before we had vaccine. So basically, in 2009, using the old way of making vaccines, like Pasteur told us, basically we're not able to be fast enough to manage a pandemic. So from 2009, the message was very clear. We need to be faster. How we could do that? This is a figure of a paper in Nature I published in 2011. And there was a vision, what was the situation to make vaccines? And you see on top, in yellow, the first line, I look at what was making vaccine in 1980. In 1980, the discovery was very long. We didn't have the tools. Science did not have the technology we have today. On the other hand, the development, the red part, was pretty short because we could license a vaccine, the hepatitis B, with 600 people. Then in the middle, in 2010, now we had a lot of technologies. We had conjugation, we had recombinant DNA, we had genomics. So basically, we could do a lot of things in parallel. And now the discovery, the yellow part, was much shorter. But in the meantime, good manufacturing practices, good clinical practices, all the regulatory things. The red line, the developer in the middle, was very long. Making vaccines now took 12, 15 years. And so at that time, I also made a prediction by 2020. Also the development, the technology is going to help development, and the time was going to shrink by doing things in parallel. And that was a prediction for 2020. I had no idea that in 2020 was going to be a new pandemic. But actually, between 2010 and 2019, the development did not become easier. So much that in the summer of 2019, we made another symposium. And we said, do we have the tools to make the vaccine development now much shorter? Can we do what we had predicted, do things in parallel? And we had people from the FDA, we had people from science. Everybody agreed we have the tools. We have the tools to make vaccines much faster, just we are not applying that. And that was the conclusion. And we said, we made a prediction that by using all those tools, we could make the vaccine development much shorter. We predicted it would be, instead of being 12, 15 years, could be 5, 6, 7 years. But we had not predicted that could be 10 months, like happened. So why was 10 months? Well, the reason to make a vaccine in 10 months for COVID basically are twofold. One, technology. And the other one is the investment from the public sector. Let's look at the technology. There were 4 technologies in particular. Here you see, starting from below, all the technology are being used from the Pasteur up to today to make vaccines. And you see that today we have an explosion of technologies, but there are 4 in particular that basically made the COVID vaccine faster. The first one is what I call internet-based vaccine. I'll have another slide about that. The second one is what a structural vaccinology, the ability to stabilize the antigens using the structure. The third one is basically synthetic biology, and the fourth one, adjuvants. So let me tell you about what I call internet-based technology. Now, I need to go back to 2013. On the Easter Day of 2013, the Chinese CDC put on the internet the sequence of new influenza virus, potentially pandemic, killed 2 people in China, and was H7 and 9. We really wanted to make a vaccine to be ready for this potential pandemic virus. But this time, instead of gathering the virus, growing the virus, and doing these things, basically what happened was on Monday, Craig Venter, that in California was doing synthetic biology, used the sequence, the genomic sequence that was in the internet to make 2 synthetic genes. That was Monday. Monday night, I was able to put those 2 synthetic genes into express mail and send those to our laboratories in Cambridge, Massachusetts. They arrived next day. Tuesday morning, we started to use the 2 synthetic genes to make 2 types of vaccines. One RNA vaccine, and the other one was basically a new recombinant virus to make a conventional vaccine. Well, by Saturday of the same week, we had 2 vaccines. We had never seen the virus. It was just made in 1 week. That was the first time that vaccines were made in 1 week from a synthetic sequence teleported through the internet. And that, from my point of view, was the transition. Basically, say, we don't need to ship viruses. We don't need to ship things around. Internet is bringing the information, and we can translate the information into products. And that was, I believe, is what I call the transition between the old way, Pasteur-like making vaccines, which are called analog vaccines because you need the virus, the bacteria, or the things, to the digital vaccines, where basically all you need is information and synthetic gene, and you have it. Now, is really digital the right word for these vaccines? Well, I think there are a lot of similarities between computers and real life. And let me show this one. You see, in yellow, you have the real life, and basically below you have what happens in computers. Well, in real life, you have DNA, and in computers, you have basically a digital code for long-term memory. Both of us, real life and computers, have short-term memory. I mean, RNA in real life and RAM in computers. Both use codons. I mean, or unit information. In real life is a codon, in computer is the digit. We all try to evade the system, and the system is, you have the hackers for computers, and you have a pseudouridine, for instance, for RNA. The ribosomes and 3D printers, they do the same thing. They translate information into products. And finally, you can think of a vaccine like a memory stick. Basically, you put information, and your body makes becomes immune. So basically, going back also to some of the things we discussed this morning, how are going to be vaccines in the future? Well, I think you can think that you can sequence pathogens everywhere in the world, get the sequence on the internet, and then we'll have centers, computers that will elaborate information, will basically design a vaccine using all the structure-based design, all these kind of things, and then it can send information to robotic stations. And all those robotic stations could be everywhere in the most remote parts of this planet. And then you have a robotic station that can make a vaccine. I mean, is that real science fiction? No, I think we have BioNTech is shipping basically more or less, they're not completely robotic, but pretty good facilities to manufacture those things to Africa. And I can think also, if you think a little bit, let's say that by 2050 we have a colony in Mars and the planet. And you have an outbreak over there. There are two ways of putting vaccines there. One is to bring physically the vaccines there. I mean, space shuttle or whatever. It's going to take 9 months. Or ship the information. It's going to go at the speed of light. In 2 days, it's going to be there. If you have a robotic station, you're going to have vaccines in 2 days. Now, is that science fiction? Maybe. But the only thing we don't have is the colony on Mars. All the rest we have. So the other thing which made vaccines very fast was really the investment from the public sector. This is the way we make vaccines. It takes $1 billion to make more or less to license a vaccine. You start with discovery, early development, late development, and every step costs a lot, and so we never do the second step unless the first one is successful. We do things sequentially. Otherwise, the companies will go bankrupt. But when the COVID came, basically this happened. The Warp Speed, for instance, in the US, has put $13.5 billion. Other money came from CEPI, from UK, Europe, Japan, other things. Altogether, maybe $15 billion. And basically, the public sector came to companies, and they said, look, I know you do vaccines the ways in the top orange things. You do things sequentially. You do phase 1, phase 2, phase 3. You don't start building a factory or a manufacturing site before you have phase 3. But this time, and you do that because you want to make sure you basically mitigate the risk of failure. And this time they said, I'm going to put the money. Here there are $13.5 billion. Every company is going to get $1, $2 billion. I want you to do vaccines the following ways, which is the ways below in the darker arrows. Basically say, discovery. I know it can take a long time, but as soon as you have the first hint that the vaccine works, do phase 1. And then as soon as you get in phase 1, I know it's going to take 18 months or 15 months to finish it. Don't wait to finish. I mean, as soon as you have the first results, go to phase 2. And as soon as you get to phase 2 and you have a good data, I know that phase 2 can last 2.5 years. Don't wait. I mean, go immediately to phase 3. And that's basically what happened. And in 10 months, we had the vaccine. The amazing thing is that we got the vaccines with taking a financial risk, which was taken by the public sector, but without taking any risk from the safety and efficacy point of view, because all the steps which are above, they were done below. And so we didn't skip anything for safety and efficacy. So that's the way we've been doing vaccines. And this is also another revolution. We learn we can do things in parallel. You can do fast. It's a question of investment. So what happened? Well, January 2020, on the left, the sequence, Chinese Center of Disease Control put the sequence on the internet. This time, there were more than 350 labs worldwide that were able to download the sequence, make a synthetic gene. And the synthetic gene was used to make 3 types of vaccines. The fully synthetic vaccines, RNA-based, fully synthetic, very fast, 66 days, Moderna was in clinical trials. Others put the synthetic gene into adenovirus vectors, and that took a little bit longer because you need to grow the adenovirus, but 3 months in the clinical trials. And below you have the more traditional way. You take the synthetic gene, you put it into a mammalian cell, tobacco cell, insect cell, make a recombinant protein, you purify. Once you purify, you combine with an adjuvant, and you have the vaccine. And that took longer, but also those vaccines are coming. And then immediately we realized that there was a difference in immunogenicity, but all of them were immunogenic. The least immunogenic, the one below, are the vector-based vaccines. The RNA are much more immunogenic, and the protein-based plus adjuvants are also pretty good immunogenic. And then immediately we got, in 2 months, basically a few months, we got efficacy. We were very surprised to see 95%. And we were happy. End of 2020, we knew that we had a vaccine, 95% efficacy, very happy. But efficacy went down with all vaccines, the RNA vaccines, the adeno-based vaccine. So what was going on? Well, and then not only efficacy went down, but the variants started to come. And we got alpha, beta, gamma, delta, and Omicron. So what was going on? And how is the efficacy of these vaccines going to deal with the variants and with the fact that and basically, in order to understand what's going on, basically we need to go back to a textbook of immunology. This is basic immunology you could find already in 1970. Basically, here what you see is that when you immunize the first time a naive population, you have what we call a primary immunization, or whether you give 1 or 2 or 3 closely spaced doses, doesn't really matter. That's still primary immunization. So 2 doses, you get an immune response, the first curve on the left. It goes up and then goes down. Few months later, at least 5, 6 months later, but better if you even wait 2 years or 1 year, now you can go back and give another immunization. That's the secondary immunization. Now the immune system has matured, and you get, basically now, you can actually boost the immune response, and now your immune response goes up, much higher than the first time, goes down again, but never goes down to the level that was before. So that's textbook. I mean, it's nothing new. Probably we have forgotten that because we were surprised about what was going on. So how you put this together, what's happening with the variants, with the immunity, it goes up and down when the variants come in. And this is a try to summarize what I believe is happening. So now, if you take the Wuhan, which is the one lower over there, for Wuhan, basically, you see the red curve, if the protection level for Wuhan is that dotted line, which is pretty low. Basically, the primary immunization gives good protection, lasts quite a long, and at some point, you may be susceptible again to Wuhan. But if you give a secondary immunization, basically the second dose, you will be protected forever for the Wuhan. Unfortunately, the Wuhan is not there anymore. So let's take another one, the beta variant, the South African variant. Well, South African variant is much more difficult to neutralize with the vaccine that we have now. So basically, the primary immunization barely was able to affect it at the top of the peak. But then, shortly after, I mean, the antibody levels go down, so people, the primary immunization did not protect at all against the against the beta. Now, if you give a third dose, probably you protect for a long time against beta. But unfortunately, by the time we gave a third dose, beta was not there any longer. Now we had Omicron. Now, the antibody level you need to protect from Omicron are much higher, 40 times higher. And now you have a problem because the primary immunization, forget it. I mean, that is not able to touch even Omicron. The secondary immunization with the third dose, you do get protection at the peak, but also after the third dose, basically the protection, the antibody levels go down. And now you have to figure out whether they will stabilize at which level in the long term. But clearly, even after third dose, you can be reinfected by Omicron because your antibodies go down. So that's what's going on. I think people are very surprised. I think what's happening out there is basically a textbook of immunology, and it's nothing strange what's happening. Fortunately, this is an infection. Fortunately, all these vaccines do protect quite well from severe disease, and that's probably the most important thing. And with that, I would like to thank you for the attention.